screen. There we go. All right, so this last problem is the same idea as the spring problem. The water is resisting the block of wood, and when you put weight on the block of wood, it's going to sink down. More weight, the more it sinks. Just like the more weight you put on a spring, the more it sinks. So what we want to do is see if we can find a relationship to how buoyant this block is, and that can tell us how much things weigh based on how much the block sinks. So let's see, we have a block of wood, 10 centimeters by 20 centimeters by 4 centimeters thick. It's floated in a pool of water, and it's submerging to a depth of 1 centimeter. So let's make a table of information and see what we can do with it. So we have weight, all that W, and we have depth. Let's call that V. And let me double check the question we're supposed to answer before I continue that. Find a linear model for the depth of the block in terms of the mass. So I have my columns backwards. So given the mass, we want to figure out what the depth's going to be. So the depth should be my Y. What did I do? Oh yeah, no, I wrote it that way. Yeah, weight is my X, depth is my Y. We're good. So let's see, we got a 50-gram mass is placed on top. So we got a weight of 50. And it's submerged to a depth of 1.25. And then we have another weight of 50 grams is put on top. So how much weight do we have now? 100. And that puts us at 1.5. Now, there's another piece of information I didn't write down. If we put no weight, then it's sitting at 1 centimeter. So first thing I want to do is I'm just going to plot those 3 points, see what it looks like. Well, let's see, scale to graph these. Maybe if I put 1 about there and then 2 about there. Oops, I put those numbers in the wrong spot. That goes this way. So 1 there, 2 about there. And then here, 0, 50, and 100. And this is important. When you make a scale and you decide that this distance right there is going to be 50, then that distance from that same distance over there got to be 52. If you decide this distance from here to here is 1, then that should be another 1 to get from there to there. So you want to make each scale like a ruler, otherwise your points get messed up. So this again is my weight, and this is my depth. Points, we've got 0 goes with 1. 50 goes with 1.25. Yeah, I got that. So that's 1.5, 1.25, so out here, and then this one's over there. Yeah, that looks like they line up pretty good. So just looking at these points, we can kind of guess a rise over run. So what's the rise and run between the first pair of points? Goes up 1/4 and over 50. What about the next pair of points? Again, it goes up 1/4 and over 50. So unlike our measurements with our springs, they were a little rougher. The points always weren't exactly the same slope, so we had to kind of guess at it. Here it looks like we have a pretty constant slope. What's the slope seem to be? 0.25 over 50, yeah. So we're getting an M of 0.25 over 50. Now here we have another lucky strike. We were given the starting point, weren't we? So I think an equation here would be that the depth is equal to 0.25 over 50. And you can clean that up on a calculator a little bit in a minute. Times the weight plus starting at 1 centimeter. Anybody got a calculator handy? 0.25 divided by 50. So maybe like 0.005 maybe. In the ballpark.
0.005.
0.005, okay. So new page. So we think the depth, oh, it's again. 0.005 times the weight plus 1. Linear model there. Now, I just want to do a little experiment with algebra here, just to remind you of some stuff. I always have to think pretty hard about which one is my y and which one is my x. X is the input, y is the output. And notice I have to look back at the problem a couple of times, look at my table and kind of think about it. So again, I decided that was going to be my y and that was going to be my x. New page. So I'm looking for an equation like y equals mx plus b because I think things line up. Instead of a y, I'm going to have a d equals m. Instead of an x, I got a w and then plus b. And then usually we get a couple of points and we find the slope. So right away we found that the slope m, by doing some subtraction on the graph, was 0.25 over 50, is that what it was? And that came from looking at those points. W versus D, so what was it, 50, 1.25, 100, 1.5. Now I'm going to make believe we weren't given the starting point and see if I can find it based on these 2 points. And the trick here is, if I don't know what B is yet, based on the points and the slope, I do have 3 numbers I can fill in here, and then I can calculate what B is going to be from there. Right? And so that's a trick we've used a lot. So I just want to review that there. So then which point should we pick? First point and second point. Turns out it doesn't matter. So somebody pick for me. Second point. So that means I'm saying that this is my y value right there, and this one is my x value right there. So for D, I'm going to say, all right, plug in the 1.5. That's going to be equal to my slope. And remember, we reduced this to 0.005. I'll use that version. Times, what's my W here? 100 plus B. And now I just clean that up and solve for B. So let's see, 100 times that is going to be 0.5. And then I can just subtract that 0.5. And sometimes that's messy and I got to whip out my calculator. Some days I can do it in my head. It kind of depends on the day. So here it looks like, yeah, B is 1, right? So now I've got the starting point. So that's a technique that's going to come in handy. Definitely going to need it on the test next week. All right. Okay, so once we have that, I think you guys can get it from here to get those other 2 problems. So I'm going to give you a minute right now, see if you can solve those other 2 problems. What's that? Oh, you weren't here the other day. Which one is this? 3.6? It is sitting on my office floor. I'll be right back. Yeah, talk amongst yourselves about those.
be 0 then?
There you go.
On 9, would you put that, would you put 0 equals?
You're missing a page on that one too. That you left blank. So if you could do that and turn back in, that would be wonderful. What's that? Yeah, but you had to write stuff down too. So you didn't write some stuff down. Did you see you got a blank page there?
Yes.
Yeah, so take a look at your spreadsheet and figure out what you need to write down there. Let's figure it out.
I think so. I didn't use math.
What'd you do in your head?
Well, it goes in 0.25 centimeters. In the water, by a centimeter.
So you've
So
got,
it should be 50 times 4, which would give you 1 gram.
so say that again. So you're talking about a change of 0.25 centimeters
Yeah.
per
50.
grams. Okay. Yep.
So if we're in the water, a centimeter, you should be 20.
So we want to know if you're in the water, because this block did sink down 1 centimeter, right?
Yeah.
And they put it in, that was the given information. Yeah. So the question would be then how many grams would have to go with that based on the slope? Yeah, that's exactly right. So we just have to solve that proportion and that'll figure out how many grams cause that 1 centimeter, and that's got to be the mass of the wood. Yeah. So this is just an interpretation of slope, right? Our slope here is always a change in that distance over a change in mass.
In the 9 though, would you set that equals to 0 because submerged?
Ah, that's a good question. Do we, in number 9, are we setting it to 0 to figure out if it's totally submerged? So draw a picture of what you think it looks like when we first put the block in the water. Got some water, and then I set a block in it. How thick is the block?
4
It's 4 centimeters thick. How much did the block sink into the water? 1 centimeter down. So there's going to be 1 centimeter down this way How many centimeters are sticking up?
3.
1, 2, 3. So the block is sticking up that far. So here's my block of wood in the water. 1 centimeter's down. So how many centimeters do we need to travel before the block sinks?
3.
3 more, because it's 4 centimeters total. 1, 2, 3 centimeters. So we want to see the block sink down 3 centimeters. If we set it equal to 0, that means the block's going to be rising above the water, which means we have to grab it and lift it up, which isn't what we're looking for. We're looking to push it underwater.
No, so if your first centimeter was, say, the block of wood, so if you figured out the block of wood was 200 grams. So then you wanted to go 3 more times, would you just go 200 times 3?
In terms of how much more weight you'd have to put on? Yeah.
And you go on.
Yeah. Yeah. You can always use the slope as a proportion to figure that out.
What do you do 3 equals 0?
You could set your formula, because your formula talks about the depth, right?
Yeah.
Yeah, so if you set your formula equal to 3, that'll tell you how much weight you need to get it down 3 centimeters further. This is number 8. $200, is that right? Yep.
Not 4.
400. So we'd have to put 400 grams on there. What'd you get?
6.
Okay, you're missing something there. What are you missing? The weight of the wood. How much did the wood weigh?
Was 200.
Okay, so
Should be.
difference between, no, because so your 600 counts the wood. If you take that off, you need 400 grams on top of the wood the way you're doing it.
First centimeter was 200. Then the other 3 should be 280, shouldn't it? 240. Because the wood itself weighs 200 grams, right?
The wood itself weighs 200 grams. Yep, that gets it
One
sinking,
centimeter.
and that gets it sinking down to this level right here.
Yeah. And then you got to go 3 more of those, wouldn't it be 3 times 200? Because there's still 3 to go, 240.
I see what you're saying. No, that's what you're saying sounds right. Okay, so
But I didn't put it in that formula, so I don't know.
well, yeah, I know. Maybe the formula's wrong. That's what I'm thinking through right now.
Work for the first 200.
So let's see. Think back to the information we were given. We got it to drop another 0.5 centimeter. Right, plus 0.5 centimeters. When we added on 100 grams. So every 100 grams is going to drop it another 1/2 centimeter should mean we get an answer of 600 grams total to drop it down. Somehow we came up with 400. So there's an error in thinking in one of those approaches, and I'm not seeing it off the top of my head. So I will get back to you on Monday about that one. That's the cool thing about math. People ask questions all the time that I cannot answer immediately. Does that sound familiar? You guys ever get stuck on homework? Good. You're not alone. I do too. Okay, so we'll come back to that. So write an answer either way and just go with that for now. We've got 2 possible answers that seem to have 2 justifications. One of them's wrong. By Monday, I'll figure out which one. If I figure it out sooner, I'll email you, I'll let you know, so you don't have to die in suspense over the weekend. Okay, so let's go back to that spring problem for a minute, and then we're going to move on to the next section. So, what's that? All I wanted in the spreadsheet is you to put your data in there and make a graph. That's all I wanted in the spreadsheet. So just on paper, you drew your data, you wrote out your data, and you made a graph. I just wanted to try to practice the same thing on the spreadsheet, just getting used to making tables and graphs in the spreadsheet. That's all. Okay.
On here, I'm going to do a spreadsheet on it.
No, only for the spring problem. The data that you wrote down yesterday from your spring measurements. Yeah, so I want that spring data for, what was that question, problem number? Yeah, so 1 and 2.
You want 1 and 2 on the spreadsheet?
Yeah, so type in your weights and your displacements for your spring, use that to make a chart, a dot plot, and that's all I want for that. All right, so I'm going to talk about what's called Hooke's law for working with springs. Hooke's law says that the mass that's placed on a spring is going to be proportional to the displacement of the spring. And I'm using the word displacement for a reason, because there's 2 ways this situation could work. You could have a platform with a spring coil sitting underneath it, and then you could put some kind of weight on top of that, and that weight is going to compress the spring. Okay, so some springs are designed to be compressed. Other springs are designed to be stretched. So it could be we have a spring hanging, and then we put a weight on it, and the spring gets stretched. Okay, so either way, we're going to have some kind of displacement based on that weight. Okay, so it could be compressing the spring, but it could be stretching the spring. And that's supposed to say proportional. What's that?
If you threw in some kind of leverage on a spring, so like it went around a 45-degree angle on a bar or something like that? How would you figure that out? It's still the same formula. Yeah, so whether, it doesn't matter the kind of spring. It could be a lever, it could be a bar, it could be a coil. So but then again, there's other physical constraints. Like it could be we don't have enough weight for the spring for us to measure it, or it could be we put too much weight and it damages the spring. So it's only within certain bounds that this works. So what that means is, to be proportional, there's 2 ways to look at that. One way is if we take the mass and divide by the displacement, that's always going to give us the same number. It's going to be constant. Okay. So bring that to a new screen. Mass over displacement is supposed to be constant. So I can clean up this equation a little bit. I'm just going to call M mass, I'm going to call displacement D, and I'm going to call the constant C. Now my variables here, oops, switch colors. My variables here are M and D, right? This thing's a constant. It's not going to change. For a given spring, it's a fixed number. Okay? And we can calculate it by experimentation. I can get the D to the other side by multiplying. So then I get M equals whatever that constant is times the displacement. Let's see, Elena, here's the next lesson. It's just about playing around with formulas. So we'll finish 3-7 on Monday and then do a little review for the test on Tuesday. And don't forget to look at the practice test online.
Gotcha.
Yeah. Test is on Tuesday, yeah. We're going to review Monday, test Tuesday. So if I happen to know a mass and a displacement, then I can figure out what the constant is for a spring. So I'm going to go grab one of my numbers here. So for example, Daisy and I noticed that for displacement 11, we had a mass of 300. So for my and Daisy's experiment the other day, we found that for a mass of 300, we had a displacement of 11. So that would be our spring constant right here. And every spring has a different constant. So I can clean that up a little bit with a calculator. What's 300 divided by 11? About 27.27. So we'll call our constant about 27.27. So that way I can figure out the mass by taking 27.27 times whatever I noticed the displacement to be. Oops, sorry, I switched to a lowercase d. Sometimes that matters. Here it doesn't. So then with my cup, what did I notice for the mystery weight? I had a displacement of 13. And usually to get that constant, people do multiple weights and lengths and then average it out, okay? Because one reading often isn't just enough. But let's say we're going to get it with one reading. So I can then figure out the mass for a displacement of 13 by just taking the 27.27 and multiplying by 13. So let's see what we get if we do that.
And you're choosing 13 because well,
because yesterday when I put my cup on my spring, it stretched the spring 13 centimeters.
so what does the 300 divided by 11 have to do with it?
To find the formula for any spring, you have to take some measurements. So Daisy and I measured yesterday that for a mass of 300 grams, we got a stretch of 11 centimeters.
Can you choose like any measurements you take, or does it have to be related to like cup?
You can do any measurements. Yeah, so usually what people do is they don't just rely on one set of measurements. They do it like we did the other day, do it a bunch of times, and they try to average it out to find the spring constant.
So you could choose like another number, like a constant, something else, and then still.
Yeah, so if I wanted to be a little more careful about that, let me grab some of this data, a new tab. What I would do to find my constant is take a whole bunch of measurements and then see what they look like. So let's see, we're doing mass over displacement. So I want this number divided by that one. And they're all going to be a little different because they're prone to human error. And so I get a bunch of different ones here. And so often what we'll do is we'll average those to find the spring constant. That's one way to do it. There's other ways to look at it too. Like we plotted a line and used the line to find the slope. Okay, so that'd be another way to go about it. So here I could just find the average. So another estimate of my spring constant would be about 30. If we wanted to try and get a little bit more accurate to see how the spring behaves for small weights and large weights, and then average it out. So calculator. So my first guess at the spring constant was 27.27. If I multiply that by the stretch I saw of 13, then that equation says my cup probably weighs 354 grams, which is pretty close to what the cup actually weighed. And so most scales before digital scales use springs. So let's see, 354 grams is what that gives me right there. And so what they would have to do is they would have to make all the springs the same way. They would have to test the springs to see if they behave the same way. Then they would stick them in the scale and connect the dial to them. And the amount the string stretched would determine where the dial moved and would tell you what your weight was. Okay, so so there's spring scales out there, and that's the way they work. And so we just played around with building our own spring scale, which was kind of fun. And all Hooke's law says is that whatever the weight is going to be proportional to the distance it stretched. And it's just a matter of experimentally calculating what that spring constant is for the given spring or set of springs, right? Like most scales, older scales use a set of springs. So this brings me to lesson 3.7. Lesson 3.7 kind of pulls together everything we've been doing in this section and is just about playing with formulas.
Are we doing this one online, or is this just?
That's the online one. Yeah, so I got to check to see if you can get your computer to use the online program.
Okay.
Yeah, that's what that part's for.
Okay.
And let's see, I didn't give some of these 7 yet. There's one for you. Two or one of them. Just one of them. Yeah, so remember, there's that page, I think it's what, page 3 on lesson 3.6 is about you trying that online program, right? And making another table and graph based on that. So playing with formulas. So one of my favorite formulas this quarter was the BAC formula. Blood alcohol content of a person is related to this formula, negative 0.015 times the hours since the first drink, plus a fraction that had 2.84 in the top, times the number of standard drinks they had, divided by their weight in pounds, times their gender factor. And G was either equal to 0.68 for a male and 0.55 for a female. Bring up lesson 3.7. And don't forget, at the end of module 3, there's an online practice midterm with 15 questions on it. And then I put up last year's exam and my written answers to each problem there, so you can take a look at how I answered questions. And yours will be pretty similar. The last year's exam was about 10 questions. The practice is 15. Yours will be about 10 questions, maybe less, so that you can get it done in an hour. Okay, so let's see. What am I looking for? 3.7. Here we go. All right, so here's that BAC formula again. I just went over and what each of the variables is. And there's a claim underneath here that if there's a male that weighs 190 pounds, then their formula would simplify to this right here. So let's double check that 0.022 is correct for 190 pound, excuse me, male. And by the way, that is about the average weight of an American male, 190 pounds. In this decade. Do you guys know average weight of people in the US has been climbing for a long time now? Interestingly. All right, so let's see, what do we know? We know that it's a male. So we want this number right here for the G. And we know that the weight is going to be 190. So to clean that fraction up, we're going to take that 2.84, that's times n, over the 190, there we go, times 0.68. And what we need to do is just clean up this part, that fraction right there, and figure out what n is being multiplied by. So on a calculator, what is 2.84 divided by 190 and divided by 0.68? Our worksheet claims it's 0.022. So we want to confirm that. So whipping out a calculator. Someday I gotta fix my Google calculator. It only doesn't work on this computer, which is interesting. So what do we get? 2.84 divided by parentheses 190 times 0.68 gives me, the 3 decimal places, 0.022. So make sure you can come up with the same answer on your calculator. So I believe for a 90-pound male, we get an equation of negative 0.015 times the hours plus about 0.022 times the number of drinks that person has. So anybody could customize this equation for themselves and make a little BAC calculator so they can make sure they're driving legal according to this formula. And it's relatively accurate. All right, let's take a look at, so you get a couple questions to answer on that. I want to take a look at the idea of z-scores, and then I'm going to shut up and let you guys do whatever you need to do. So in statistics, there's an idea called a z-score. And so I just want to explain what each of these things mean. It says it here, but I'm just going to re-explain it. So anytime we collect large amounts of data, we looked at this at the end of chapter 2, data. We often summarize the data by doing things like calculating, like, what's the average? What's another name for average? Mean, correct, the mean. Often we use the letter, it's a Greek, it's called mu. It's Greek. And it kind of looks like a cross between an M and a U. So that's the Greek mu there. And that's the symbol you see a lot for average of some data set. Now, another important idea in data is trying to talk about the spread of the data. How spread out is it? Because there's lots of data sets that are going to have the same middle, and some data sets might be tightly packed, other data sets might be way spread out. Okay, so it just kind of depends. Like if you looked at the height of a bunch of basketball players, you think that data is going to be pretty spread out or pretty tight? It's going to be pretty tight. They're mostly tall people, right? Not too many short basketball players. However, if you just grabbed your average group of students, would the heights of those students be spread out or tightly packed? Maybe be spread out. There's going to be tall people, there's going to be short people, there's going to be people in the middle. So another thing we would like to calculate with data is the spread of the data. And there's a lot of ways to talk about spread. For those of you who go on to Math 105, we'll play with it there. We'll play with it again in statistics for anyone that keeps going. One way to talk about spread is an idea called standard deviation. Deviation is a lot like displacement. Deviation just means distance from the middle. Right, so how far, so if the average height of a guy in the US is, let's say 5'9", I'm 1 inch below average. So my deviation in height is 1 inch. Standard deviation is kind of like an average deviation, an average spread of the data. Bigger the standard deviation, the more spread out the data is. Smaller the standard deviation, the tighter packed that data is. Okay? So the idea of a z-score in statistics, it's a count of how many standard deviations a measurement is from the center, from the middle, from the average. So I'll just give you an example of that, and I'll show you the formula, because this is a pretty important formula. Anytime you look at data sets, usually standard deviations and z-scores pop up. So all a z-score does is count how many standard deviations, how many average deviations is some score from the data given a big data set. So let's say for US males, and I should have looked this up ahead of time, that average height is 5'9". And that's what we call the mu for the data set. And let's say the standard deviation for height, let's say that's 3 inches. That's usually given the Greek letter sigma. So if I look at a number line, here's 5'9", right? If I go 3 inches to the right, where is that going to put me at? 10, 11, 12. It's going to put me at 6 feet, right? And if I go another 3 inches to the right, that's going to put me at 6'3". If I go 3 inches to the left of that middle, that's going to put me at what, 5'6"? And if I go another 3 inches to the left, that's going to put me at 5'3". And usually what happens, about 95% of individuals are going to be in between those numbers. Most people are going to be within 2 standard deviations of the data. So my height, I'm about 5'8". So if that's 5'6", 5'7", 5'8", this is me right here. Am I a whole standard deviation below average? No, I'm just a part of a standard deviation below average. What part of a standard deviation would you guess? I'm 1 inch below average. What's a standard deviation here? 3 inches. So I'm 1/3 of a standard deviation below average. That would be my z-score. Okay. So I am 1 inch below average. No, percentiles are a different idea than z-scores. That's a different way of talking about spread. Yeah, and then when we get to that Math 105, can't remember if we get that in Math 105. It's certainly a big topic in statistics, which is Math 243. Yeah, so percentiles are another way of talking about spread compared to standard deviation. But sometimes we use them together. Like here, I'm using them together. So here, if 95% is in the middle, That leaves 5% on either side. So there would be 2.5% left over on this side. So someone that was 5'3", they're in the 2.5 percentile. There's 2.5 on this side percent of people. So what's that? 97.5% of the people are here or lower. So someone that's 6'3", they're in the 98th percentile of heights. Okay. Someone that's 5'9", they're in the 50th percentile of heights because that's right in the middle. Yeah. So they're related. It's just a slightly different way of talking about it. So 1 inch below average is the same thing as having a z-score of 1/3. Now let me show you the formula quick on that. Sorry, I used up all our time here, but this is an important idea. To calculate a z-score, what you do is find the deviation. All deviation is take a measurement and find out how far away from the mean it is. And then to count standard deviations, you just divide by the standard deviation. Okay? So for example, for me, I'm 5'8". Average is 5'9". Now it's usually safer to convert that to inches, but this isn't a hard one to do. Standard deviation is 3 inches. So 5'8" minus 5'9", that gives me that -1 inch that I am below average. Right, so here's my z-score of 1/3. That's all a z-score is. It's just accounting in terms of this idea called the standard deviation. Standard deviation is like the average spread of the data. Okay. All right, so that covers about half of 3.7. Work on that stuff for homework. We'll finish this up on Monday and review for the test. Don't forget, check out those practice exams this weekend. Please.